Thank you for tuning in. Hello and welcome to today's webinar, where we want to take a closer look at the specific aspect of our recent CAESES 5 release, namely the efficient optimization of existing geometry models with morphing. My name is Matthias Brenner, and I will be your host and moderator today. I'm currently responsible for sales here at Friendship Systems, and I'm joined by a few colleagues for this webinar. In order of appearance, we have Hedi Böttcher, who is a support engineer, as well as our marketing manager here at Friendship Systems. Then we have Heinrich von Sado, who's also one of our support engineers and a specialist for maritime applications. And finally, Carsten Fütterer, who's also support and applications engineer here at Friendship Systems and our expert specifically for powertrain and turbomachinery applications. Before we actually get started, I have a few housekeeping issues that I want to mention. So today's webinar will be recorded and then available for replay later on. So you will get an automated email one day from today with a link to access the recording of the webinar. And later on, we will probably also share the webinar on YouTube on our website. Also, you have the possibility to ask questions, which we will try to address at the end during our Q&A session. You can submit these questions throughout the webinar, starting from now or at the end in the webinar interface, and then we will collect these questions and try to answer as many as possible at the end. So for the people who are not familiar with CAESES, just a few words of introduction about our software CAESES. So CAESES is basically an optimization platform, shape optimization, mostly in connection with CFD, flow simulation. And CAESES consists of three main components. The first one is a CAD environment, which is a specialized CAD system with a strong focus on geometry variation, especially of complex geometries, often freeform geometries that are typically difficult to parameterize in other CAD systems, and with a focus on robust variation and different other aspects that we will also talk a bit more about later. The next component is a generic interface that is used to connect CAESES to external simulation tools. As I said, this is mostly CFD simulation tools, but can also be tools from other disciplines. And finally, the optimization environment that provides all the necessary tools to run an automated optimization process, which means the algorithms and post-processing capabilities, data management, and so on, everything that is needed in that respect. So today we want to talk about morphing, and before we start that, I would like to draw a small comparison between morphing and parametric modeling. So when we talk about parametric modeling, or more specifically what we call fully parametric modeling, we mean the generation of a parametric model for either the complete geometry or at least a component of the geometry from scratch. And we have parameters, a set of parameters that define all the features and properties of the final geometry. The advantages of this approach are that we have a very detailed and exact control over all of our shape properties, and also an important advantage is that we can integrate constraints very well. So if we have constraints due to manufacturing reasons, packaging, whatever it is, there we can take them into account very well into the way the geometry is parametrized, and even make sure that these constraints are automatically fulfilled for all the geometry variants that we create. The disadvantages of this approach is that it's more time consuming. You have to invest a certain amount of time to set up this parametric model from scratch, and also needs a know-how about how to efficiently parameterize things, how to translate a certain idea into a parametrization. On the other hand, we have a morphing approach, or what we also sometimes call partially parametric modeling. Here we have typically an existing geometry that comes maybe from another CAD system, and we import the geometry and define parametric deformations to this geometry. So the geometry itself is not completely defined by parameters, but only the changes to this existing shape are defined by parameters. And the advantages here that it's usually quite quick and easy to set up, and also often intuitive. You just have certain ideas in mind what you want to change, and you can translate that into certain deformations, transformations to the geometry. The disadvantages, and here I want to point out before we released CAESES 5, because these are topics we have tried to specifically address in our new release. But anyways, the disadvantages here were that you have only an indirect control over the shape properties, as you control only the changes to the geometry and not the complete geometry. It's more difficult to control certain aspects of the geometry, as well as constraints that you might have on the geometry. So if we look at, again, the situation before CAESES 5, we also had different morphing capabilities, and specifically objects in CAESES that allowed the transformation or morphing of existing geometries. The first one was the so-called delta shift. This is a displacement of the geometry controlled by a curve function. So you can see here in the animation we have a curve, and when we move this curve, the geometry is deformed according to the displacement of the curve. This is a nice approach, can be combined also with other curve function, delta shift functions to apply weighting or limit the deformation region. One disadvantage here is that the displacement is only possible in principal axis direction, so in either X, Y, or Z direction. The second approach that was available so far was the so-called surface delta shift. This is basically the same approach as the delta shift I showed before, but instead of having a curve displacement function, we have a surface as a displacement function, as you can see in the picture here inside of the bulb of this ship. And again, this is also limited to principal axis directions. Then we have a more specialized transformation, which is called a Leckenby transformation. This is dedicated to maritime applications, specifically ship hulls, and this allows a change of displacement volume and the distribution of displacement volume. So yeah, it's just really application specific. And then we have so-called freeform deformation. Here the geometry is controlled through a box that surrounds the geometry, and this box has vertices, and we can move the vertices of this box, and the geometry that is inside of the box will also be transformed according to the space around it. So you can see it again here in this example. This, as you can imagine from this description, is only a very indirect control of the actual geometry changes. And also sometimes it can be tricky to set up a suitable box to surround the geometry that you want and to allow the deformations that you want to do. And then finally we have two, let's say, a bit more exotic or experimental implementations we had in CAESES before, called the Cartesian shift and spot shift. These are essentially point-based sources where you have a deformation in a certain radius around them. I called it here experimental implementation. I don't know if this is the right word, but at least it's not something I think that someone was really using. It's cumbersome and impractical to apply to realistic problems. So when we released or planned CAESES 5 and implemented CAESES 5, we had different motivations. First of all, we think morphing is a great tool for beginners with CAESES and shape optimization. So basically you have the situation that you want to optimize a certain geometry and you want to you don't have experience with parametrization of complex geometries, so I think this is a very great entry-level tools. So we want to provide more tools that are easy to use and are still powerful for this approach, and that are also applicable for all kinds of applications, because what I showed before came from our maritime heritage, and many of these functionalities are well applicable to maritime situations, but maybe not so much for other applications. So this was one motivation, and as I mentioned before, morphing does have certain disadvantages, or the morphing implementation we had so far had certain disadvantages, and we wanted to reduce these disadvantages by providing a more exact control of the shape deformations and also for taking into account constraints, and basically moving the morphing approach closer in terms of advantages and the possibilities to what we do in the fully parametric approach. So in CAESES 5, we implemented new morphing methods that are based on radial basis functions. Mathematically, I think it's not so important as a user what mathematical method it is, but just for you to know the background. And there are essentially two different methods that are available. We have the interactive definition of deformations with basically a paint tool, as you see a little bit in the animation here, where you can define area where you want to change the geometry and move the geometry. And this is currently applicable only to discrete geometry, so tessellated geometries like an STL import. And then we have a second approach, which I think is even more powerful and flexible, which provides deformations that are based on source and target geometries. This can be applied to NURB space geometries as well as discrete geometry. And basically, as you can see in the animation at the side, you select certain let's say we have curves as source and target, and then you can select certain feature lines of your original geometry as source, and then you can create derived geometries as target. So another curve, like here, the shifted line, the green one, and basically then you can morph the geometry from the source to the target. And this can be applied to all kinds of different applications. Here we see it for an external aerodynamics application. This is the modification of a ship stem. Also, there is a slight difference to the one before. Before we had a fixed target and then we just moved in between the source and the target. Here we have a moving target that takes the geometry with it. And even to maybe a little bit our surprise, this is also very well applicable to even turbomachinery applications, where typically before we would never have recommended a morphing approach, because in these applications it's very important to precisely maintain certain properties like airfoil shapes or thickness distributions, tip gaps, things like that. You needs to be all maintained very exactly. But now with this new morphing approach, we are able to fulfill these requirements and can even apply morphing productively to turbomachinery applications. Okay, that's so much for a short introduction from my side of and also history of how this functionality was developed. And now I would like to switch over to my colleague Hedi, who will start with a first live demonstration to show you how these methods are actually applied on a real case. So let me switch over.
Yes, thank you, Mattia. I'd like to get started and show you how this mesh morphing or the interactive paint morphing can be applied to any kind of geometry we can import in CAESES. So let's start by importing an existing geometry here. And in this case, I'll choose an IGES import. So we can see the mirror appearing here we want to use for our mesh morphing. Once this appears here, we can see that this is my IGES import I used. It's a side mirror of a car, and maybe not the most typical application we have, application case and CAESES, but it's still an easy and nice example to show you the mesh morphing capabilities here, which can be applied in the end to any kind of geometry. So if we create a morphing object, the mesh morphing is the part here where we can interactively change and paint parts of the geometry. So I've created this mesh morphing object. The imported geometry, my original mirror, is set as an input. So if I apply this, I can see that this actually becomes a tessellated geometry here. So if I hide the original one, I can see that my mirror here now becomes the tessellated geometry, which I want to use. So I can create a region. And if I go into this edit mode, I can enter this paint environment here. So I can mark the deformation area with this brush or paint tool here, and then just simply draw on my geometry, just like this, in a nice intuitive way, easy to choose. So if I want to, let's say we want to pull this part a little bit up. So this blue area is my deformation area, so the area I want to be considered in the modification. So if I place a vector handle here, which is the easiest way of applying a deformation here, I can just place it on my deformation area and then simply deform this with a vector handle. So I can pull the vector handle up and down, and I can see that my geometry follows along quite nicely. I can also define the magnitude of this vector here and give this an exact value for my deformation, which I want to apply. So this is a nice way to modify this very easily and very, very quickly. I can also create a parameter for it and give this an upper and lower bound here. So I could use this little slider to actually move my geometry up and down and define the deformation that is applied to it. So let's look at a different application case maybe, or not different application case, but let's say we want to extend this connection part here and modify the area here in between without actually changing the diameter or the profile of this connecting section here. So let's look at this and create another region for it. We'll go with this vector handle approach again, and then change into the edit mode. And this time, okay, this radius of my painting tool is a little bit too big maybe, so I can press Control and then use the middle mouse wheel to change the size of this brush radius tool here. So I want to mark my deformation area around here. Just paint it in, which is blue, which is the marks the modification area. And then since I do not want to change the actual shape of this end part of this connecting part here, I can choose the rigid motion area brush and make this a little bit smaller, and then paint the parts that I do not want to, that I want to shift, but I do not want to change this in the shape. So let's see how this ends up here. Okay, so now we have the green, the rigid motion area, which should be shifted but should stay the same in shape, and the blue area, that's the modification area that can kind of flow and be modified in the direction we would like to. So if I place a handle on this rigid motion area here, I can change the orientation of my vector handle. And then let's say I want to pull this way, and then like we did before, can pull this in and out quite nicely with this vector handle approach. So this is a really easy and fast way to set up modifications to any kind of existing geometry that you can import as a IGES step or STL file. And then this comes in especially handy when you want to stay with a tessellated geometry in the end and keep working with it. Okay, so with that, I'd like to give it to my colleague.
Thank you very much, Heidi, for this demonstration. You can really see how easy and quick and intuitive it is to define some simple deformations here. So now I would like to transfer to the next presenter, which is Heinrich, who will show some additional methods for deformation, and let's make him the presenter.
Yeah, thank you very much, Mattia, and also Heidi for the nice demonstration. I would like to follow up on that with an application from the maritime world. I've brought along this sport boat propeller here. Again, this is also, just as in Heidi's case, an imported geometry, and I would like to mainly focus on the BREP morphing in this demonstration, but I will also give a small introduction to the mesh morphing with this application here. So what I've imported is obviously just 1/5 of this propeller here, and I'd like to focus on this part here for the modification of my geometry. I've prepared this a little bit, but as Mattia has already said in his introduction, BREP morphing mainly is based on the definition of source and target geometry. This could be source and target points, or source and matching target curves, or even surfaces. So most of the modeling in this type of modeling is essentially the definition and the parameterization of these source and target curves. And I've made life easy for me in that I've just chosen to use these existing curves of my geometry here, which are the curves that define the topology of this blade. That's how it was generated. There's the suction and pressure sides, and up here there's the tip region, and in between those there's just a split of the individual patches. And what I've done first is I've defined myself this axis here, which ranges all the way from the very tip of the blade to the axis of rotation of the propeller. And then I've used this axis as an axis of rotation of this green section that I've just described. So I've created a design variable called delta pitch here, which allows me to rotate that section around the axis. And this way, I will later be able to add or reduce the amount of pitch of this propeller blade in the tip region. Next up, I've defined myself this helix, which I've just manually adjusted. It's just eyeballed to roughly match the pitch of the initial propeller. And I'm using this helix in a sweep transformation so that I can add skew to my propeller blade. And I can just sweep my curve along the helix. And of course, I can do both at the same time. So I can add pitch or reduce pitch and add or reduce the amount of skew that I impose on this blade. And then finally, I have a very simple translation defined here. It's just a shift of this curve in actual direction. I've called this rake because this is what you would call this in propeller design if you bend your blade upstream or downstream. And with these three design variables and the two curves, the source and target, I have everything at hand that I need to define a Birab morph. I'm just going to delete the existing one here so that I can just show you how easy it is, in fact, to set something up. So we'll use my imported geometry, come up here, choose a Birab morphing object. The source curve is source object, sorry, is automatically assigned because I have had it selected. If I hover here in 3D view, I need to turn on dynamic highlighting. I can see that the faces 10, 11, and 12, that's the two blade faces and the tip, are the ones that I actually want to modify. So I can enter them here. And then, like I already mentioned, all I need to do is define my source and target curves here so that the Birab morph would know from where to where to shift the geometry. And as soon as I enable the morphing here, you can see that we get a new blade that perfectly matches the transformed blue curve. I've prepared a little visualization here in which I can add my Birab morph so that we can see a little bit better the difference between the initial geometry, that's the green surfaces here, and then the newly generated silverish gray propeller. And if we play around with our design variables, you can see that the propeller follows along nicely. It's a very performant model, actually. It goes very quick. We have a nice variable radius fillet at the bottom of the blade here, which stays exactly where it is. Continuity is maintained, and that's why the model is very fast, because we don't have to regenerate all of these solid operations here. If I turn on isofolds, you can see that the surface quality is very good, very high, very smooth, even though I apply quite substantial amounts of shape variations here. So this is hopefully showing you the level of intuitivity and also performance, how such modifications can be set up. And it's actually all you would need to then run an automated study, maybe a design of experiments here based on a Sobol algorithm, where I can choose delta pitch, rake, and skew, the design variables we've defined before. I can set up a little screenshot collection, maybe if I wanted to, and then just run this. And in just a matter of a few minutes, I'm able to generate this model and generate different shape variations, which I can then assess, maybe run a few simulations on them, or just look at them, compare them, see how I like the modifications in shape here. Let me switch over to the design viewer, where we can find the resulting geometry variants that we've just generated here with the Sobol algorithm. If we browse through here, you can see that there are actually quite some changes in shape between those geometry variants. And now finally, to finish this off, I would also like to set up a mesh morphing based on this propeller geometry. So let's say we choose the modified geometry. It's the Birab morph we've just generated here. And off of this geometry, we now want to generate a mesh morphing. as Mattia has already mentioned, and I think Hedi said that as well, the mesh morphing is based on discrete geometry. So this is detached off of the original geometry, if you will. And we've seen this in Hedi's demonstration also already. We can now very easily use this paintbrush tool here to define the region that we actually want to modify and the region that we want to keep fixed in place. Can add again the vector handle here with just a few clicks. Maybe orient that handle to an angle of rotation to our liking. Try and adjust this from a couple of different angles here. Maybe a bit more like this. And then we can move that handle. And as you can see, this allows us to very easily set up a tip brake propeller model, which is something those of you who are involved in propeller design would know is actually not that easy to achieve if you use the common approach of radial distribution functions of pitch and rake and skew and all the other propeller properties, because you would generate sections on concentric cylindrical surfaces. And if the amount of rake at the tip of your propeller is too much, you're losing the shape properties you've defined in those sections. While with the mesh morphing, as you can see here, it is very easy. With just a few clicks, you can not only deform your geometry, but actually also, again, as Hedi has shown, parameterize it so that you can then change the amount of deflection that you would want to see here. So from -4 to 0. And this is how easy we can set up a design variable. And then again, we could run a study, generate variance automatically, or even run an optimization and try to minimize cavitation and volume and things like that. And with that, I would like to hand back over to Mattia. Thank you very much.
Yeah, great. Heinrich, thank you very much for this impressive demonstration here. I think it's easy to see how much flexibility these tools allow. And I think we want to explore this a little bit more in the next demonstration from Karsten, who will also focus on the BREP morphing tool for another application. So let me switch over to Karsten.
All right. So with this application or example, I want to show you at the BREP morphing the 3 different types of sources you can set, and show you also a little bit the, let's say, advanced options to set up the BREP morphing. So to start with, I want to show you the morphing with a point. So therefore, I create basically on the original geometry a point. I first select a face of the imported intake port, and then I go to surface based, and then I create a surface normal point. This is basically first my source, and distance is 0 because it's the source, and the position should be something like 8,5. So there's just this position here, so that we modify this shape basically of the port. Then I just copy and paste that point, make it target, and let me put the distance to a design variable, change the bounds to, let's say, -2 to 2. And then you can see, so this point is basically now normal to the surface. We could also have a different design variable like the position, for instance. For instance, we could create design variable like this, and then we can change the position of that point. Let me put that back to 8,5. All right, so so we have source and target defined. So let's now create the Webmov object itself. First, I select the imported model, then I go to Morphing, create the Webmov. This will create the geometry. Now it is important to hide the original geometry because now they are both overlapping, and sometimes that can result in some conflicts when you select some faces. So I hide that. Now we have to select basically the faces which should be morphable. So I go to this tool here, button, and basically what I do is I'm entering the edit mode of that BREP. You can also see that in the orange bar here, at the bottom, sorry. And now I just draw a rectangle and select all these faces because all these faces now should be used in the deformation. And now I activate this toggle and leave the edit mode. So you can see now these faces which are morphed change the color. And additionally, you see basically next to these faces, you see these red points, and these red points basically indicate the boundaries to the faces which are not morphed. And these basically take care of the tangency between the surfaces. So let's select the Webmov again. And also one thing you actually always have to check first before you enable it. You have to have a look at the control polygon, because all the morphing itself behind the scenes will work on these individual points of the control polygon. So, and if it's too coarse, the morphing will not be working or won't be really exact. So in this case, I definitely have to refine it. So I use an absolute not spacing here, something like 5. In my example, it's a good value. You can see now we have much more refined geometry. So I can leave that mode, and now I can use my source and target point here and here. All right, so nothing has happened right now. So now I can enable basically the geometry. Let me enable the morphing. You can see how the morphing will now take place to that. Okay. Maybe also one thing to know is you have these fixed geometry options here, where you basically define the behavior on the boundaries of the patches you morph. For instance, you can define how many of these red dots you can use, or for instance, how strong the magnitude of that tangency should be. So for instance, when we put the tangent scale here at the side, it will be really high magnitude to the bounds of the boundary. All right, so let me remove that. It's just for you to see the difference. All right, so now we can use the points as source and target curves. Curves as source and target geometries. Therefore, I have already created a folder here, and what I basically want to do is I want to create a curve on the bottom of the port with some offset distribution to it. So I have already defined a normalized offset curve here in 2D. And now what I do is I create a offset curve to that. I use that surface, which I already used here. So you can see it's a little bit shorter at start and end. Let me put that at working scope. Now I go to surface-based, oh no, not points, but curves. So isoparameter curve with offset. So my source curve will be this. I switch the domain, put the parameter to 0, and put the distance also to 0. So this is basically my source curve. I put the parameterization here to unit speed, because it's also really important to know that basically the difference between source and target geometry will be based on the parameter values. So if the parameter values of source and target are pretty different, then your result won't look like as expected. So let me copy that and paste that. So I have my target. And here I don't use a constant offset, but I use a thickness curve, which I have already defined here. This, and with a thickness factor of 10. All right. So you can see when I zoom in, I have this offset at the later part of the surface, and I can change here, for instance, the offset to 2. I can change the start position. That will basically be that position here. So like something like this. And the offset position also with the maximum offset. And yeah, so then I can use these curves in my BREP object. I just drag and drop them here. As you can see, you always have to make sure that these sources and target matches. So in the first part of the position of the offset object list, you can find the point. Second part, now the curve, and so on. So each source and targets have to match. So let's look here. All right, so now you can see how the BREP morphed. Let me change that parameter, for instance. So quite easy, and you can really nice thing is that you really know what the BREP will do. You give a certain target, and the geometry will follow. That's pretty nice. So in the last step, I want to show you how to use surfaces, because they're also pretty cool. If you want to, let's say, for instance, move, for instance, this whole port here at the inlet, and keep, for instance, this complete surface here fixed. So let me create a surface from the original port. So just select that face here and create an image surface. Maybe call that source. And based on that, I will create a target surface. This is my target. And here, with the help of the post-processing operations, I can create a transformation and a translation. And for instance, I can create a design variable for the Z location. Maybe put a value from -10 to 10, for instance. And then this surface will move up and down. All right, so now we can use that source and target surface here in our source object list and in our target object list. And then I can show that again. And you see now how the BREP basically morphed along the translation of that surface. And the nice thing is really that along the surface, the shape will basically be as the original shape. That's pretty nice. All right, maybe a few words for more additional options here. We have the interpolation factor, which is basically you can blend between source and target with a factor. You can also extrapolate, so I can also make 0.5. This will now just have the half of the transformation. And then you can also find here some solver options. So usually this can make that also more smaller in order to be more accurate. And you can also use something like 0.9 in order to have a more exact fitting to the target. And in the end, basically after the morphing has been applied, you can also reduce the data again, which you have increased before the morphing. You know, remember you increased the knot spacing here in order to have a good morphing, and at the end we can basically reduce that basically again based on a certain tolerance. So we can go here to post-processing and say, okay, we want to reduce the data again to match maybe that tolerance of the geometry. And you can see all this part now is, has been reduced again. So that's pretty nice. I think that was it from my side.
All right, great. Thanks again. An impressive presentation of the capabilities and some more things that you can do with this tool. So now I would like to summarize what we've seen a little bit, and I'm gonna switch over to myself. All right, so as a summary, we have seen the mesh morphing, so-called mesh morphing. The mesh morphing is applicable to discrete geometries. So for example, if you have imported an STL file, within the mesh morphing, we have available the interactive paint and pull method, as I'm going to call it here. So the interactive method where you can paint areas of the geometries to be transformed and pull or push with a vector handle. As well as the source and target methods that we have also seen later on. It is very quick and easy to set up, especially if you use this interactive method. If you just want to very quickly define some deformations to the geometry, it works quite well as a variation for geometries that you are able to use in a tessellated format. So as an example, as an STL file that might be used as an input for a simulation. So in that context, you can use this method or this tool very well. But since we are working with discretized geometries, it would be difficult to feed back into a CAD design process. So if you have an STL file, a deformed STL file, depending on the CAD tool you're using, it might not be so easy to feed back into the design process. On the other hand, we have the so-called BREP morphing, and this is applicable to NURBS-based surface geometries. Currently, for the BREP morphing, we have, in quotation mark, only the source and target method available, which is quite powerful, as we have seen in the examples before. So still provides a lot of flexibility, as well as we've seen exact control over the shape of the geometry due to the way we can define a target geometry that we will match exactly with our deformation. We can control very very exactly where we want to end up with our geometry. The geometry in the end can be exported in many different NURBS-based formats like IGES, STEP, ACES, Parasolid, and so on. And due to these formats and it being a mathematical surface definition, it is significantly easier to feedback this optimized design or modified geometry back into your CAD design process. All right, I think that's so much for our presentation part, and I think we have some time left for questions. So I'll be more than happy to answer these questions and my colleagues as well. Let me take a look at what we have received here. We have one question here. If you have an imported STL that you're modifying, does the deformation change anything to the coloring of the STL or of the tri-meshes that we have imported? Does someone know the answer here?
I can answer. So no, this is the coloring is kept constant or as from the import.
Okay, so this is, I think, good news, which I think maybe not everyone is familiar with the coloring, but this is a way to identify different patches of the geometry, especially in your downstream simulation tool, to apply mesh settings or boundary conditions. And of course, I think it's important if these colors are not changed. Another question here regarding the interpolation factor. I think, Carsten, you touched on that. Here there is a question if you can explain a little bit more how this interpolation factor works and yeah, what the possibilities are, or Heinrich, whoever feels like it.
I haven't used it in my presentation because I have set up design variables to change my target curve so that it would match the initial source curve or then be different from that. But what you could also do is use the interpolation factor. That means you have source curve and a different target curve. And if the interpolation factor is 1, that means 100% deformation. So you're exactly matching the target curve, as exact as you set it in the solver options, the advanced settings that Carsten has shown. Yeah. While if you set it to 0.5 maybe, that means 50% of the deformation. So you're somewhere in between. And the interesting part here is that you can actually have also a negative deformation factor, or you can also extrapolate. So you can go beyond 1 to 1.5 or 2 or something like this. So it's really just the source and a target point or curve or surface. That's all you need. And then you can use the factor to have a parametric model that resembles anything in between and even outside of these bounds to be used in optimization or any kind of study that you want to run.
Yeah, very good. Another question here that maybe I can quickly answer is whether you can use the morphing together with freeform deformation or other techniques within CAESES. Yeah, that's most definitely possible. Basically, you can combine whatever methods you want. You can combine morphing with a fully parametric model. You can combine these BREP morphs or so with something like a freeform deformation or delta shift. So any combination is possible. But of course, there might be situations, so if you have a fully parametric model, for example, and you apply some mesh morphing, then of course the end result will be just a discretized geometry. If your fully parametric model was a surface model before, at the point where you switch to the mesh morphing, you will lose the connection to the parametric model. But otherwise, I think there is many possible combinations. Let's see. There is a question here whether the morphing can also be applied to potential flow penalizations. I believe this is currently not possible. Currently, we can just apply it to tri-meshes in CAESES. So if you are a CAESES user, you're, I guess, probably familiar with tri-meshes as objects. These are triangulated geometries, so this does not cover potential flow penalizations. But I think there is still room for further development, and we have definitely planned to extend these morphing capabilities also to other types of data, which also includes specifically CFD meshes, and of course might also include things like a potential flow penalization. So again, at the moment it's not possible, but maybe something that will be added in the future. There is a question here regarding the BREP morphing, whether the BREP morphing is ideal for locally adding or removing volume for a ship geometry. And whether just one source and target line are enough to maintain curvatures, tangencies on the surface. Maybe
I can answer that again.
Maybe Heinrich, you have an opinion.
The answer is definitely yes. We've seen that in your presentation. We've also seen that in the recent webinar on more general topics of CAESES 5. So there's many applications in ship design, especially in hull design, where the morphing can be used and can add great value. For example, I've recently used it a lot to do modifications of stem shapes, of the contour of bulbous bows, of the waterline and entry angle, things like these. You can cut your ship at the waterline and define yourself a new waterline that you would like to match. These kind of things. All of this is possible. Keep in mind that also morphing from one surface to another is possible. So if you think just matching two curves is not enough, there is the option to match two surfaces to one another. And then about the continuity, the answer is also yes. That's exactly what we had in mind when developing this functionality, that you would want to map from source to target while maintaining continuity towards the remainder, towards the stationary and non-modified part of your geometry. And as Carsten has shown, there's also options there to change the number of these continuity points. That actually, in the background, what that means is that you change the level of continuity. So having just one point means you have just a watertight gap there, or no gap, a watertight connection. While having 2 points means you keep tangent continuity, having 3 points means curvature continuity, and so on and so forth. And then you can set the spacing to change how that continuity is distributed into the surfaces. So I hope that answers the question.
Okay, great. Thank you, Heinrich. There is one question here which maybe goes a little bit into specific detail. This is for a powertrain application. Which method would be most appropriate to modify imported valve seats and combustion chamber just in radial direction if the intake port would be fully parametrized? So, I don't know. I can maybe say already a few words for it. I think if you have your imported geometry coming from a NURBS-based format, so you have that comes from an IGES or a step import or something like that, then I think the BREP morphing would be the best solution here, where you can really define the changes that you have in mind here with the source and target geometries. And I think also it would probably work well to combine it with the, as you mentioned, the fully parametrized intake port, because you could use parts of this parametric model directly, for example, as source and target geometries to for example, move your valve seats or change the valve seats if you change your parametrized geometry. So I hope this answered the question. I'm not quite sure if this is exactly what you were aiming at, but I think for everyone who asked questions here in general, feel free to contact us also afterwards if you want to discuss some things in more detail, and we would be happy to follow up with you. We're also coming towards the end of our time, so I would just finally want to address a final small question, which I mentioned before at the beginning. If the video recording is available for this webinar, yes. Everyone who registered for the webinar will get a link to the video recording in 24 hours from today, from now. You will get an automated email, and you can rewatch that video, and then later on it will also be probably available on our YouTube or something like that. So if you liked what you saw here today, what can you do next? You can download CAESES 5 on our website. If you are not an existing user, you can register for a trial license and test CAESES 5. Of course, you can watch out on our website for announcements of upcoming webinars. We will, I think, have some more webinars about specific functionalities in CAESES 5 in the near future. And of course, if you have questions, or as I said, if you would like to discuss any topics with us, you can contact us through the contact form on our website or through info@friendshipsystems.com. And apart from that, this is all we have for you today. Thank you very much for attending this webinar. Stay safe and stay healthy, and I hope to see or hear you soon. Goodbye.